Imagine an autonomous vehicle traveling at highway speeds in total darkness. When an obstacle suddenly appears, the system has only milliseconds to respond. At this scale, even a tiny sensor delay or a power clash between radar modules results in a failure to brake. The result is a high-speed collision. The root of this failure isn't found on the road, but in the engineering office. Historically, complex system requirements have been tracked across thousands of fragmented spreadsheets and text documents, creating isolated information silos. This fragmentation leads to model rot. When one engineer updates a component, the change often fails to propagate through the rest of the blueprint, leaving the entire design based on a lie. The catastrophic physical failures we see in modern machines originate as invisible contradictions in the design phase, long before manufacturing ever begins. To bridge these silos, the first generation of model-based systems engineering relied on visual diagrams. These were essentially pictures drawn using software engineering languages. But because these tools were built for software, engineers had to map physical energy flows and mechanical parts using static communication symbols. This created ambiguity, as different teams could interpret the same diagram in different ways. SysML version 2 moves past these subjective drawings. It shifts the focus toward coding machine-readable architecture that a computer can actually understand. Managing modern complexity requires a transition from visual approximations to writing mathematically verifiable code. Traditional spreadsheets treat technical values as simple text strings. To a computer, a cell containing 10 kilograms is just a label. It has no inherent meaning or physical context. This chart compares the two approaches. In SysML version 2, data is explicitly bound to the International System of Quantities. The machine understands 10 and kilogram represent physical mass. Because it's machine understandable, it uses standard APIs to serve data across the engineering ecosystem. SysML version 2 creates live data links to external tools. If an engineer increases a part's mass in the main model, the system instantly recalculates technical performance metrics across every connected analysis tool. This live synchronization forms a digital thread, where every data point actively maintains the system's integrity throughout its entire lifespan. At its core, the system uses a framework called KerML, which is built on first-order logic. This allows the model to mathematically prove its own viability. Consider a satellite power budget. A design might include components that require 110 watts to operate, while the solar panels are constrained to provide only 100 watts. A traditional diagram might visually hide this flaw, but a logic solver reading the code will instantly flag the contradiction. When the requirements exceed the physical constraints, the logic engine identifies this as an empty set of realities. Mathematically, this machine cannot exist. SysML version 2 functions as a mathematical lie detector, stopping fatally flawed designs from ever leaving the computer. Modern systems are dynamic. They exist and act within a specific Shigongan space-time context. SysML version 2 introduces 4D modeling, which treats every part and every action as an occurrence with a specific duration and location. For an autonomous vehicle, engineers use this logic to code strict constraints on sensor data freshness. They can mathematically define exactly how old a data point can be before it becomes dangerous to use. By applying latency constraints to the sequence of perception, planning, and actuation, engineers can guarantee the vehicle reacts within a safe time window. Treating time as a verifiable mathematical constraint allows us to guarantee physical safety margins using pure logic. This code-based model serves as a single source of truth, capable of communicating directly with factory floor robots and digital twins in the field. Because this architecture is written in logical text rather than drawings, large language models can read and write it directly. This enables generative MBSE, where AI can instantly convert natural language requirements into complex, verifiable architectural code. The AI can simulate thousands of design variations, checking each one against physical laws to proactively block contradictions before they ever reach a human reviewer. Now, the engineer moves from drawing diagrams to programming systems architecture, partnering with AI to mathematically prove the safety of our most